Hello everyone, good day. My name is Daud Mariam Omowunmi, and today I'll be presenting my research titled Computational Modeling Design of Novel NMDAR Agonist for the treatment of schizophrenia. I would like to give my sincere appreciation to Beyond Science Initiative for giving me the opportunity to share my findings with you today. Schizophrenia is a complex and chronic mental disorder affecting millions worldwide. It presents with three main categories of symptoms: the positive symptoms, including delusion and hallucination; the negative symptoms, such as anhedonia, alogia, and social withdrawal; and the cognitive deficits, affecting attention, memory, and problem-solving ability. Despite current treatment, many patients experience limited relief, necessitating the search for novel therapeutic approaches. Role of NMDAR in schizophrenia. The N-methyl-D-aspartate receptor, or NMDAR, plays a crucial role in brain function by regulating calcium ion influx, which is essential for synaptic plasticity, neurotransmission, and memory formation. NMDAR hypofunction leads to reduced calcium signaling, weakened synaptic connections, and disrupted neural circuits, contributing to schizophrenia symptoms. One promising approach to treating schizophrenia is enhancing NMDAR activation using glycine-mimic co-agonists to restore receptor function, improve synaptic strength, and manage symptoms. Existing NMDAR co-agonists, such as glycine, D-serine, and D-cycloserine, have significant limitations, including low blood-brain barrier permeability. Thus, it requires high doses, short half-life, and rapid metabolism. They have toxic side effects such as nephrotoxicity and hyperexcitability. This research aims to design novel compounds that cross the BBB efficiently, exhibit higher binding affinity to NMDAR, and demonstrate low toxicity with improved pharmacokinetics. The research followed a structured computational drug discovery program, including generation of ligand datasets using Data Warrior, preparation of target protein with PDB ID 5HF8, followed by molecular docking screening using standard precision and extra precision, ADMET toxicity analysis for drug likeness and pharmacokinetics profiling, then lastly molecular dynamics simulation to assess the stability of the best performing compounds. 10,000 ligands were generated from Data Warrior, and it was screened down to 4,736 ligands based on molecular weight and blood-brain barrier permeability. The 4,736 ligands were subjected to molecular docking, both standard precision and extra precision, in order to remove extra forces. Standard extra precision docking algorithm shows that 3 compounds have better binding affinity compared to glycine, and compound 945 to be the compound with the highest binding affinity of -9.0 kilocalorie per mole. The 3 compounds were subjected to ADMET analysis using high-drug tensors, and the ADMET analysis confirmed favorable pharmacokinetics with high blood-brain barrier permeability, said compound 15 to have better BBB permeability compared to compound 945, and compound 945 have better permeability compared to compound 8. They also showed to have good oral bioavailability, low plasma protein, binding for better drug distribution, and no significant toxicity risks. Molecular dynamics and simulation. The 3 compounds were, including the apoprotein, were also subjected to molecular dynamics and simulation at 100 nanoseconds, and molecular dynamics simulation validated the stability of compound 945 which had the lowest RMSD value, the root mean square deviation at 0.23 nanometer, indicating strong and stable receptor binding. We have minimal fluctuation, the root mean square fluctuation, the compact structural integrity, the radius of gyration, then through the 100 nanosecond simulation and see stable hydrogen bond interaction, enhancing the NMDAR activation. These are the compounds selected. These are the selected compound, and the compound with the best binding affinity, better Agonist profile analysis, and better stable structures compared to glycine. The Agonist toxicity profiling of the selected compounds with glycine shows that compound 15 has better blood-brain barrier permeability compared to others with 0.93 value, followed by compound 945 with 0.82 and compound 8 with 0.81. Also, the selected compound also shows better oral bioavailability compared to glycine, but most especially the compound with the highest binding affinity, compound 945. Also, they also show better human clearance compared to glycine. Compound 15 shows better, the highest, and compound 8 also show better human clearance compared to glycine. Also, for molecular dynamics and simulation, we address 4 parameters: root mean square deviation, root mean square fluctuation, radius of gyration, and hydrogen bond. For root mean square deviation, R remains the value. It helps to understand the stability of the ligand and the rate at which the ligand deviates from the active site of the protein. From this result, compound 945 shows the lowest deviation from the active site of the protein with 0.23 nanometer. And for the root mean square fluctuation, it helps to understand the rate of fluctuation of amino acid residue. And from this result, compound 945 show minimal deviation compared to other complexes. Radius of gyration helps to understand the compact structural integrity of compound at the active site of the protein. And from this result, compound 945 also shows better compound structural integrity compared to other compounds. And also, hydrogen bond analysis confirms stable interaction, further supporting its role in NMDAR activation. In conclusion, compound 945 demonstrated the best binding affinity, stability, and higher blood-brain barrier permeability than glycine, ensuring better brain uptake. It also exhibited low toxicity and favorable pharmacokinetics, making it a promising NMDAR co-agonist. Computational drug design effectively identified compound 945 as the best candidate for further preclinical studies. Thank you for listening.